The point is to see how cycle number of curve C sub alpha changes as alpha decreases from 1 toward 0. The parameter alpha is defined on the interval from open 0 to closed 1. So 0 is strictly less than alpha, and alpha is less than or equal to 1. We don't allow alpha to be 0, since then the curve would collapse to a point. This way C sub alpha is always a curve. Also, notice that the family of curves C sub alpha is continuous in alpha. If we have, say, alpha equals 0.5, then for alpha equals 0.4999 enough nines, C sub alpha will be everywhere very close to C sub 0.5, which means for every point on C sub 0.5, there will be a point very close on C sub 0.4n9s, and vector field at those 2 points should point in very similar directions, given that vector field has a minimum length. So cycle number for C sub 0.5 and C sub 0.4n9s should be very close, but cycle number is integer valued. Now this should look strange to you. Cycle number as a function of alpha appears to be both continuous and integer valued. So how can it change? Cycle number of C sub 1 equals 1. Does that mean cycle number must be 1 for all values of alpha? Well, no, that's impossible, as we'll show now using the minimum length min. All right, let's say that this distance is min, the minimum length the vector field can take, expanded so you can see clearly. Since vector field is continuous, if we have a point P and we draw a small circle around P, all vectors in this circle must have heads close to the head of P. In particular, we can choose a circle so small that all heads of vectors in this circle are within distance 1/10 of min of the head of P. And the circle itself is meant to be smaller than 1/10 of min. Make min a little bit bigger to make that work out. Okay, cycle number equals 1 means that at some point on a curve, every direction must be represented somewhere with a vector pointing that way. That's what it means to make one full cycle. So if this small circle must have cycle number equals 1, there must be some point on this circle where vector field points this way, and its length must be at least min. And there must be another point on this small circle where vector field points the opposite way, again with a length of at least min. So, if this small circle must have cycle number equal to 1, we have this situation. And how far apart are the heads of these two vectors? Well, it's going to be min plus at most 2/10 of min. So certainly the heads of the vectors will be more than a distance min apart, but this circle was chosen so small that no distance difference of bigger than 1/10 of min was allowable. So, a small enough circle must always have cycle number 0, given that there is a minimum length min. Which means that as alpha decreases from 1 to 0, cycle number must jump down from 1 to 0 in spite of being continuous. So, contradiction. The assumption of a smallest length, min greater than 0, was false. Our theorem is true. We may not know where the fixed point is, but we know there must be one, or more. Hooray! We've done it! That's how proof by contradiction works, and it seems like something's missing somewhere. So let's look at what actually happens when cycle number starts out as 1 and alpha decreases. We now drop our false assumption that there is a minimum length for vector field. The theorem is true, and vector field does have 0 length at some point, the fixed point. And for ease of understanding, let's get rid of that vast ambiguity in the crumple function. The theorem is true for a large family of complicated crumple functions, so we're going to pick a specific one, supercrumple. Supercrumple says the top sheet has been compressed to a single point. Sorry, I can't demonstrate that. So top is now a single point in 3 space, which is projected down into a single point in bottom, which we'll call x for unknown. I'll draw it. I drew it. You'll see it in a minute. So the heads of all vectors in vector field are at x. Every vector points to x from every point in bottom. Our theorem is true. 3-step of x equals x. X is our fixed point, and vector field of x has length 0. So now what happens to cycle number as alpha descends from 1 and the curve c sub alpha gets close to the point x? Let's imagine a value of alpha where the c sub alpha curve comes within 1/100th of an inch of point x, but still contains it. Point x lies barely within the curve c sub alpha. And for a slightly smaller value of alpha, where the c sub alpha curve comes equally close to point x, but this time x is outside the curve. Now here's an example, expanded, so you can see what's going on. So here's point x. The blue curve contains x, and the red curve does not. This drawing is not to scale, or you couldn't see the interval, but let's see how our cycle goes. Remember, vector field always points to x. So let's do the blue curve, and I'll show vector field with the blue pen. Okay, start at this point, where the direction is close to straight down, and let the point move around the curve this way at constant speed. The direction of vector field is slowly rotating clockwise, as it always points to x, and it moves around the curve until, say, it gets to this point, almost all the way around, where vector field is pointing close to straight up, having rotated through 180 degrees, a little more. Then, in the remaining small length of curve, vector field rapidly rotates the rest of the way around to complete one cycle, one clockwise cycle, and cycle number is 1. Note that the direction of vector field is changing very fast when the length of vector field is very small. So it seems that as alpha decreases to almost touching point x, cycle number stays equal to 1. Now let's do the same thing for the red curve. This curve is very close at every point to the blue curve. So let's start at the point where the direction of vector field is not quite straight down, over here. As before, we move around the red curve this way, always pointing to alpha, and we see that the direction always pointing to x is making a clockwise circle as before. I was forgetting to point to x. Okay, here we go. Till we get to about this point, almost all the way around, where the vector field is pointing not quite straight up, having rotated almost 180 degrees. But this time, the clockwise rotation halts, and the fast rotation starts in a counterclockwise direction, like that. In a very small length, the direction rotates almost 180 degrees counterclockwise, undoing all the previous rotation. The cycle number of this c sub alpha curve is now 0. And similarly, cycle number will stay 0 as alpha continues on down arbitrarily close to 0. Now let's look at the point of closest approach. The two curves are 2/100ths of an inch apart, and the direction of vector field is exactly opposite here versus here. But that doesn't violate continuity since the length of vector field is so small. So in the small part of the curves, where vector field's length is small, its direction rotates quickly in opposite senses. And that's the difference between cycle number 1 and 0. Now, what we haven't done is, what about the curve that goes exactly through point x for an alpha value between the red and blue curves we were just looking at? So we go around as before, then what happens at x? The direction of the vector becomes undefined. There's no way to say which way, clockwise or counterclockwise, it goes around x. So cycle number is undefined for that critical value of alpha that goes through the fixed point x. This is the loophole we need to have a continuous integer-valued function with a jump. As alpha decreases from 1 towards 0, the curve's cycle number is 1, 1, 1, undefined, 0, 0, 0, 0, 0. The cycle number function is continuous everywhere it is defined. So it seems that though a vector must have magnitude and direction, like in the movie Despicable Me, when it has almost no magnitude, it doesn't much matter which way its direction is. And this points out a fundamental difference between rectangular and polar coordinates. In rectangular coordinates, what does the line x equals 0 look like? It's a vertical line through 0. What does x equal 1 look like? The same vertical line moved over. Essentially the same thing, even though one goes through the origin and the other doesn't. It's the same line. But in polar coordinates, there's a singularity at r equals 0. Direction becomes meaningless. The system breaks down. If you're standing on one of the Earth's magnetic poles, your compass will not tell you anything useful. Polar coordinates are great for many applications, especially navigation, but you should keep in mind this singularity exists at r equals 0. This could be a Zen koan, when the wind blows not, from which direction does it blow? For completeness, the one case we haven't covered is what if point x just happens to be on top of the point center? Maybe not likely, but there it is. Then, as alpha decreases from 1 towards 0, the cycle number is 1, 1, 1, 1, 1, 1, 1, 1, 1. It never changes. Remember, alpha is always greater than 0. It can never be 0. Vector field decreases in magnitude towards 0, but never reaches 0. So in this case, cycle number really is equal to 1 for all values of alpha, but there is no minimum length for vector field. The theorem is true, and x, or center, is the fixed point. So, I hope you enjoyed our little journey to a fixed point, and seeing what mathematics was hiding in 2 innocent sheets of paper. You will be encountering more fixed point theorems in other contexts as you learn more, and most of them have this same approach, proving the fixed point exists without actually finding it. Sometimes that's all you can do. And as you use polar coordinates, which are quite handy for many applications, remember the singularity at the center. I'm Phil Rennert. Have a good day and enjoy your fixed point.